Hi, everyone. In the 6 red card examples we've seen, we talked about a one-tailed analysis where we calculated the probability of getting 6 red cards out of 6, and a two-tailed analysis where we calculated the probability of getting 6 cards of the same color, whether red or black, out of the first 6 cards. And we'll do one-tailed and two-tailed hypothesis tests throughout our class. But what's this deal with tails? Why are we talking about tails? I'm going to talk about this in the context of coins, but as a setup to that, when might you want to use this idea of tails in example 1 or example 2? Let's say that in the first 6 cards selected by the students, let's say that 5 of the 6 cards were red. 5 of the 6 cards. Would it be enough to just calculate the probability of 5 red cards or 5 black cards? I would suggest that you would need to consider the cases of 6 red cards and 6 black cards as well. I'm talking tails. If that's not clear now, let's talk about a coins example. Why tails? Why do we discuss tails at all? Example 3. Let's go back to the magician's coin. David gives you a magician's coin, and it's going to be flipped 100 times. Technically, the ingredients for the hypothesis test, the null hypothesis, the alternative hypothesis, and alpha should all be predetermined before you get your sample data. So we're waiting. A magician's coin will be flipped 100 times. Okay. So what is the null hypothesis? What is the natural default hypothesis assumption you fall back on that you can base probability calculations on? What should be the null hypothesis? The coin is what? The coin is fair. That's the null hypothesis. The alternative hypothesis, H sub 1, is that the coin is not fair or biased. What do we observe from the sample data? Let's say you now take David's coin, you flip it 100 times, and you get 59 heads out of 100 flips. This might take you back to when you did that pink extra credit sheet, right? When you were flipping coins. Let's say you got 59 heads out of 100 flips. That's our sample data. Now, here's where the probability comes in. How unlikely are our sample results under the null? Well, now, a lot of students might say, well, I guess I'd calculate what's the probability of getting 59 heads out of 100 flips. What's the distribution, by the way? What is the distribution in play here? If X is the number of heads you get when you flip a presumably fair coin 100 times, remember we base calculations under the assumption that the null hypothesis is true, under the assumption of a fair coin. What's the distribution at hand? It's a binomial. X would have a binomial distribution where n equals 100 flips or trials, and assuming a fair coin, which is what the null says, P, the probability of heads, would be 1/2. And again, a student might say, well, I guess I could go to Excel and ask Excel, what's the probability of getting 59 heads? Or use that wacky formula. Well, let's go to Excel.